Hello there, Mr. Sutton here, bringing you the BC Calculus 7-7 Extra Practice Number 2 solutions on geometric, nth term, and ratio tests. For this problem, we're trying to figure out if this series converges or diverges. Now, there's a few ways to start this one. This is a geometric series, so you definitely could go with the geometric series test. You could also, I always like to start with the nth term test. So the key here is figuring out whether this ln of 2 term is more or less than 1. So ln of 2, that's going to be less than ln of e, which is like ln of 2.7 and some change. We know ln of e is 1. So that means that ln of 2 is actually less than 1. So if I take the limit of this expression as n approaches infinity, that means that this expression here is going to be getting smaller and smaller. The denominator is going to keep shrinking and shrinking, which means the fraction as a whole is going to keep growing in size to infinity, which tells us, since this is not 0, that this series diverges by the nth term test. For this one, I'm trying to figure out convergence for a series. Now, just going through my list of tests here, it's definitely not geometric. The denominator is, but the numerator isn't. The nth term test, this is a bottom-heavy fraction. 2 to the n is growing much faster than n squared. So this will pass the nth term test. We can't disqualify it based off of that. So really the only other thing that's left at this point is the ratio test. So let me take the limit as n approaches infinity of absolute value of the n plus 1th term over the nth term. So that's going to be, let's see here, n plus 1 squared minus 1 over 2 to the n plus 1. All of that over just the original formula in there, the original nth term. And now, if I same change flip this thing, I end up with, let's see here, this 2 to the n is flipping upstairs, so we've got 2 to the n times n plus 1 squared minus 1, all of that in the numerator. Denominator, we have the 2 to the n plus 1 and the n squared minus 1. These exponential terms can cancel a little bit, so if I subtract the exponents, that leaves me with just a 2 downstairs. And I can go a little bit further now. If I expand everything here, the dominant term in the numerator is going to end up being an n squared. In the denominator, we're going to have a 2n squared, and all the other terms grow more slowly, so we can just ignore them as n goes to infinity. So now I can just reduce this to 1 over 2. Since 1 over 2 is less than 1, that means that this series is going to converge by the ratio test. On this problem, figuring out convergence, as always, let's begin with the nth term test. So as n approaches infinity for this expression, we can ignore the slower growing term of 1 downstairs. So this is really n over 2n. And then we can just cancel the n's. So this is just 1/2. Since 1/2 does not equal 0, since the nth term's limit is not 0, that means this is growing without bound and diverges by the nth term test. For this problem, I want to know whether this series converges or diverges. I'm going to try the nth term test first. So as n approaches infinity for this thing, we keep flipping back and forth between positive 1 and negative 1, and we can't really decide. So I'm not really sure that there's any limit here. I'm going to write plus or minus 1, which either way does not equal 0. So this thing is going to fail, miserably fail, the nth term test, which means that this series does diverge. To find the convergence of this series, we're going to try first the limit test, the nth term test. So limit as n approaches infinity, we'll just use this general term here. So as n keeps getting bigger and bigger, we keep alternating, but also getting further and further away from 0. If this thing did have a limit, I guess you could call it plus or minus infinity, if that's even a thing. In any case, it's not 0. So this fails the nth term test, and thus it diverges. As we go through our list of convergence tests on this one, we see that this is going to go to 0 if you take the limit as n approaches infinity, so it passes the nth term test. The next easy one is the geometric test. This is a geometric series with an r value whose absolute value is 1 over 8. So since the r value, the absolute value of that is less than 1, that tells us that this is going to converge by the geometric series test. For this one, we're trying to find the summation of 1/3 to the I. I is our index variable here, with an initial value of n. So in order to find this, it helps to recognize that this is a geometric series. That means if we know the first term and the common ratio, we can find the sum of this, assuming that it actually does converge. There is no option here for not converging, though, so it will converge. It's just a matter of what it converges to. So our first term is going to be whatever we get when we plug in this this lower limit of summation. So that's just going to be 1/3 to the n, which seems kind of weird, but n is treated as a constant here. It's just a constant we don't know the actual value of. Our common ratio, that's the thing that we keep multiplying by over and over again. That is definitely 1/3. So then I can write my infinite geometric sum formula. And before I do that, let me just confirm that this does converge. So since this has an absolute value for the ratio of less than 1, we are going to converge on this. All right, so now that we've gone through that proper etiquette, let's go ahead and find the sum. That's going to be a1 over 1 minus r. So 1/3 to the n over 1 minus 1/3. And let's see here. We can simplify this a little bit to get an answer choice. 1 minus 1/3 is 2/3. And if I same change flip this thing, we've got 3/2 times 1 over 3 to the n. Is that one of our answer choices? That looks like choice C. On this problem, we're trying to find the sum of this infinite series. So we got to be careful here because there is an option for this series diverging, so we'll have to check into that question as well. But one thing that would be helpful on this problem is recognizing that we are just multiplying by the same thing over and over again. We have a geometric series. The first term of this series, well, it's right here. It's pi over e. No surprise there. The common ratio, what we keep multiplying by, it looks like we're multiplying by 1 over e, or at least negative 1 over e. It keeps changing. But the absolute value now of this common ratio, 1 over e, that absolute value is going to be less than 1. Because e is bigger than 1. So this means since I have a common ratio less than 1, we're going to converge here by the geometric series test, which is great. But what do we actually converge to? That's the next question. So really all we've established at this point is that it's not choice D. This definitely converges. To figure out what it converges to, we use the infinite geometric sum formula, S equals a1 over 1 minus r. So we have our a1, that's pi over e. And 1 minus r, this is actually going to be using the actual r value, not the absolute value. So this is going to be 1 plus 1 over e down there. And of course, that's none of the answer choices, so we have to do a little fraction simplifying dance here. Let me start by combining the terms in the denominator. So I need a common denominator between these. I can rewrite this as e over e plus 1 over e, and then combine it to be e plus 1 over e. And now if I same change flip, I've got pi over e times e over 1, or e plus 1. These e's are going to cross cancel, so we just end up then with pi over e plus 1. And that matches, let's choose this carefully because these all look so similar, choice B.